Hello, and welcome back to the live stream. So in the last stream, we added support for braced initializers. We're now able to create an array and initialize it all in one go. And as we can see, so we initialize the first two elements were 1 and 2, and then the last one gets implicitly initialized to 0. So this happens here as well. But if you look at the generated assembly, it's a lot. And the reason it's a lot is because the initialization, what essentially is doing is going on is something like this. So we take array 0, set it to 1, array 1, set it to 2, and then we are calling memset on the remaining elements. So we're setting it to like so. So that's essentially what we're doing, right? So here we're storing 0, then we are getting the next address, storing 2 in there, and then we're calling memset. The function isn't, it's our own built-in, so it doesn't know how to print it, and that's a bunch of code. And I've looked at what actual compiler are doing to initialize arrays, and instead of doing it like so, what the compiler is doing is they generate like a global constant array init that contains the appropriate elements, and then they are mem copying it over, right? And that's neater assembly. So let's change our initialization code to also do that. So for that, we need to adjust CodeGen. So where we initialize the array, CodeGen init right here. So first of all, we are calling the built-in lauf memset. I've since added a built-in to lauf itself. So essentially this implementation. So we instead can call lauf lib memory fill, which takes 3 arguments. So the destination, the byte, and then the count. So here we also need the byte that we're using to fill, which is 0. Right, and then same deal here. Also calling the library function. Right here. Of course, you don't know what memcopy. Okay. And so this one still works. We initialized it to 0. And now what we can see is that we are calling, where are we calling it? Here, lauf memory fill, base remaining address right here, 0, 8 bytes. So that works. And then the, so let's commit that. Lauf lib memory fill function. Okay. And now for the complex initialization, we want to create a global constant. And then copy stuff over instead. So what do we want to do? Essentially, we want to do constant evaluation of this loop. Then we get a bunch of bytes. Then we store those bytes in a global variable, and then we copy stuff over, right? So let's do that. Const eval right here. So we've got constant eval for a type and an init function, and returns a number of bytes. That's essentially it, right? Except that of course we can't call that function because it calls CodeGen init recursively. So what do we do here? Let's do a bit of a hack. So can we essentially detect whether we are currently doing constant evaluation? Because if we want to do constant evaluation, then we generate this loop. And if we don't want to do constant evaluation, then we instead generate a copy. Right. So let's add a parameter bool during constant evaluation. So if we are doing constant evaluation, so the recursive calls pass them through. Yes. So if during constant evaluation, then we generate this loop. Otherwise, we want to actually okay. So during constant evaluation, we do that. So this is the naive code that manually initializes the array. And if we're not doing constant evaluation, then instead we want to do constant evaluation. Constant eval context type ourselves. That way we get bytes. And then we want to add love Adam add string, build string literal. So we want, if we have two arrays initialized to 1, 2, 3, we don't want to create two globals. Instead, we want to create only one and reuse the storage. And this is particularly common with string literals, where we also, like, if we have the same string multiple times in the program, we don't want to generate multiple storage addresses for those. So we can use a function that builds a string literal and deduplicates it. So this is simply the, of course, the interface isn't ideal because it assumes that we're having a null terminated string, and I need to reinterpret cast here. Char from unsigned char. So this is something that can be improved in Love's API. So this gives us a global. And then instead of, so now we've got the global containing those bytes. And we now just want to copy that one over. So for that, we're calling memcopy, memory copy, which takes destination source address. So destination is already on the stack. This one is the source is the address of the global. And then we want the size of the array, which is, do I've got the layout already? Array size. Array size times element layout size. Let's call you data. And then when we actually call the function, we just need to set the correct flag. So this one does constant eval of an init function during constant eval. So this generates the naive loop. And then the other call, we are passing paths over there. This one is fast because we are not doing constant eval. And we are calling an undefined function. Okay, which isn't ideal. So codegen init. That's the wrong target. Release mode takes a while to compile. So we're having an assertion failure during the backtrace. That's not good. And before we are calling right here, we're in the panic handler. Due to the because we're calling an undefined function. So the IP here. So we're inside a call instruction, right? So why is the right here? So we are somewhere. So we're in the call instruction, and for some reason we want to call a native function, and then we reach this panic. But why do we want to call a function native function at all? Right. So apparently, okay, that's interesting. So I just noticed that we don't have any bytecode. So main is the function that we're calling, which doesn't have a definition. And that one's also wrong. So something's messed up. So that's supposed to be the initializer of our global. Of our array, I mean. And it doesn't have the correct value, right? It should be 1 to 0. Instead it is, oh, right, because it's a C string. So as soon as we have a null byte, it's stopped. So that's the first issue. So I do need to add a new API. Okay, so let's do that. So we're calling here build string literal, which assumes a null terminated string, and obviously the bytes aren't null terminated, right? So that's the first issue. So let's get over to low and continue working here. So we've got the function build string literal. Same as above, but initializes it with constant bytes. Let's actually use that order. So build constant, yeah, let's call it a data literal or something, right? So it contains arbitrary data. That's deduplicate. Constant pointer, size the size. It's a constant global containing the specified data. Specified data to the module of the builder that contains the data. Already, if it exists, returns that address, otherwise adds a new global. Like so. As above. That's just all returns log Adam build string literal b string string. Because that's essentially what it's going to do. And then inside the builder, so build string literal. So it's currently literally a very naive that does naive comparison. Size 1 pointer. So we're doing a loop over everything, check until we find something, which isn't like the nicest implementation, but let's see. And then we want to define it. So the alignment of a string literal could always be hard-coded to 1. Let's just make the alignment of the value like here, layout, so like the pointer alignment or whatever. And then we are calling the data literal b reinterpret cast to unsigned char the string colon string +1 +1 to include null terminator. I'm guessing so +1. So that's a simple function. And now then build data literal. So let's use you. And then we are calling build string literal instead. We're already calling it build data literal. Bytes.data, bytes.size. And we don't need the null here. Okay. So now need to fetch the new version, so it takes a while. That needs to rebuild the entire loaf library. And now we're here. So now we're getting, which looks like the const bytes. So we've got like 1 and then 7 zeros and then 2 and then 7 zeros and then probably 8 zeros at the end. But we still don't have a main function, which isn't ideal. So why are we not having a main function? Right. So are we not calling codegen function body? We are. And its name is name. So we are calling it. We are starting building it. Need to construct all the lambdas. Then we are finishing it. So starting with an op instruction. So we have some instructions. We want to emit a linear body. Does that one work? Yes, we added 27 instructions. We are setting that. We're returning and having still 0 instructions. Why is that? Oh, I know why that is. So the issue is that while we are so we're building the function, we're adding a bunch of instructions, and then right here we're doing constant evaluation, which reuses the same builder and starts building a chunk. And then we are discarding every instruction we already have and instead start building the chunk. So we need to actually, so we can't call constant eval during, right. So this is why originally we had 2 builders in the context. Like a builder for regular code and a builder for constant evaluation, and then we can use the correct one depending on the flag. I wonder, can we do it better? Yeah, I think that's still the way to go. Like the design, I'm not quite happy with the fact that we're calling this function recursively in a different context, and then we get the correct data, and then we, right, that's not nice. So we might be able to fix that, restructure that somehow, and then we can avoid that issue. But I can't think of something. So instead, let's just do a quick hack to see whether that fixes the issue. So we are setting a new builder. Which we're then just drawing up a constant evaluation and resetting the builder back. And now that one, thanks, should fix, yeah, it fixed the issue. So then we got 0, 1 to 0 by mem copying those bytes into the array, right? So that's all the initialization now. We get the address of the array, we get the address of our global, we get the size, and we copy it over. Okay. So creation of a builder is expensive. This allocates a bunch of memory, so it's nice if we're able to reuse it. So let's get the thing again where we're having two builders. So we've got the body builder for building a function body, and then the chunk builder for building a chunk. And right, so and then we're passing the current builder to a parameter. So that was the design we already had, but we refactored it a while ago. But it's really apparently still the correct design. So passing the builder to all functions. So the builder here is the chunk builder. Let's just follow the arrows. So this one here is the current builder. This one here is the current builder. Current builder. Current builder. And the current builder. And then here we want to get a builder as a parameter, and then we also don't need the boolean because we can compare the builders instead. So if the builder is context.chunk builder, then we are at compile time. Otherwise we are at runtime. Oh, not const. Right. So instead we're passing the builder along. Codegen function body and uses the body builder. Codegen init, again, we want to here use our current builder. Right, and then we want to initialize it. So we've got body builder and chunk builder. Body builder, chunk builder. We're destroying both of those. Chunk builder. Yeah, let's just follow the remaining errors. Body builder is a builder and the chunk builder is a builder. Body builder. I don't like that we're passing like so many members to this context in multiple places. And getting codegen init. So here we are doing constant evaluation, but we can still pass, and based on the builder we can detect that. Codegen expression as internal linkage isn't defined. That's because it now takes a builder, which we then need to pass. which we then need to pass. Right, and so that one is not works. So we implement a better way of array initialization by evaluating the initializer at compile time, and then copying it over. Except that one obviously doesn't work if we can't evaluate the initializer at compile time, I just realized. And I'm guessing like there isn't a rule in the C standard that says like that isn't allowed, right? Yeah, so we get a, yeah. I'm guessing Clang. Let's see whether Clang accepts it. Which is like nicer way of then manually verifying the standard. Yeah, that's allowed. So we need to support that. So I'm guessing CodeGen init. So we're having an array, and we are currently doing constant evaluation, or can evaluate at compile time init. So if we are currently doing constant evaluation, or if we can't evaluate it, evaluate the initializer at compile time, we need to manually initialize each array element. Otherwise, we can evaluate the initializer, store it as global memory, and copy the values over. So let's write the function can evaluate at compile time. Do I maybe have something like that? Is constant. Hey, I already have it. It's spelled as constant init. Right. Makes sense. So instead of that, or not, 0 is constant init. Right, and why are we getting 2 twice? So we're storing 42 into the local address. And then the initializer at line 4. We're storing a 1. We're storing a 2. And then we are getting the local address again. So what we're not storing the value, we are storing the address of the thing. So that's actually a bug during CodeGen. So if we look at here the decal statement, the braced initializer, the expression in it is the identifier expression A, which is incorrect because we need to do an L value to R value conversion, which we're not doing. So during the compiler, somewhere we are creating the initializer. We're creating a braced init from the init thing. Right, so right here, when we have an expression initializer, we need to do L value conversion of that thing. Which, right? So now we're doing L value conversion, which means we're properly decaying the array A into assigned in 64. Which means we're no longer storing the address of the thing, but its value, which means we are getting 42. Okay, so that's actually a different bug. So let's commit that separately. Ensure L value conversion in initializers, optimize braced initializer to use constant evaluation when possible. Okay. So that's that. What I now want to do today is support the incomplete array types. Right? So in this particular case, they can be deduced from the array initializer. So let's see what the standard has to say. So we've got array declarator right here. So we've got array declarator as an optional assignment expression, which then creates an incomplete array type. This size is not fair, and the array type is incomplete. Right. So let's just support it in parsing and go from there. So we've got the array declarator grammar somewhere in here. And then we've got the square bracketed assignment expression, which is optional. So we've got a square bracketed optional assignment expression. This means that we are now having an overload where we don't have an expression. So if we're having an expression, then we want to do all of that. Otherwise, we want to create an array declarator without a size. So we've got the array declarator without the size. Let's just say zero-sized arrays aren't a thing. Well, I mean, they are a common extension I might want to support. Let's not worry about it. So let's just say a zero-sized array means incomplete. Yes. So we've got the array declarator, and then we've got the array type. And let's add a getter. Bool is incomplete. Return size 0. Okay, so I've got the function is complete object type, which of course an array isn't, an incomplete array isn't. So if you're having an array, scene of array type, then return array is incomplete. The matching function call. Right, apparently this is the callback for the declarator. So apparently we don't have let's just say I thought this was so. Let's try that, maybe. No. Okay, let's see the error message. Right, requires 2 arguments, but we were provided. Requires 2 arguments, but we requires 2 arguments, but we were provided. Right. Conversion candidate of type. Nope. Requires 4 arguments, so we've got 3 arguments. Wait, really? We don't get that one? That seems like a bug in Lexi. That we're not getting anything for the... Yeah. So apparently when we don't have an expression, we're not getting anything, even though we're using opt here. This one, this thing. If we're having the terminator, then we could use null opt. Wait. So why are we not getting null opt in the callback? I wonder. Because, no, well, doesn't matter. Okay. So while we're at it, when we are creating, so I just realized something that currently nothing is stopping us from doing that. So we're not checking. Yeah. So we're getting a weird location here. But okay, let's commit that for now. So support incomplete array type declarator. Then let's try getting a proper error message for that. So, oh. Wait, now you're getting null pointer. What? Hang on. So we are getting null opt. So what's going on here? So we've got a caller that calls it with 3 arguments only. Who's doing that? Yeah, skipping 96 contracts. Yeah. Okay, I'm not going to debug. This is clearly a bug in Lexi. So let's just do that. To do, why do we need this overload? This is a bug in Lexi. Okay. Right. Unhandled non-scalar type. So we're triggering a bunch of to-dos and instead of getting an error message. Apparently we're checking it here. Okay. So let's amend the commit and try to figure out where's the best place to do that. So when we are, so we've got this function type get type or something, this one that creates a type, and at that point we're creating an array type right here that may have empty size. So who's calling that? A bunch of places. So we would I think the best way. So the issue is that at this point, here we know that we're having an incomplete element type, but we don't have any facility here to generate an error message. So I could just say if the error size is 0, let's return null pointer, and then we check for null pointer. But then we don't know what sort of error occurred. But given that I can't think of anything like at the moment, so we create like anything else is valid. Like you can create a pointer to an incomplete type. If you're having an incomplete type, if the type itself is incomplete, that's fine. And we can use any type here in a function declaration, right? So let's just let's not worry for that for now. So if we're having let's, instead of calling child type, let's call it element type. So if the element type is incomplete, so it's not a complete object type, and then we're returning null pointer, right? Constraints, the element type shall not be an incomplete or function type, right? Okay, and then just everything that calls it needs to check for null. So right here, the pointee type can be null pointer. If it is, propagate. The element type can be null pointer. The return type can be null pointer. Yeah. Right here, that's fine. This one can return null pointer. What's it doing? Type name and parents, right? So we need to check that. If decal is null pointer, then we're returning the that thing. I'm not sure what this logic is, but I don't care. Otherwise, if you are null pointer, then we are returning, creating just a generic message, invalid combination of base type and declarator. And return type. And then we just need to copy this error message in a bunch of places. Location of that's a bit annoying. That so first of all we need a position, which is like fine. So get a position. But then, right, the rest of the thing assumes that we are having already a type, so I can't really do an early return here. Because what would I return? So we don't have type. So let's just say the type then is int. Just so we like the rest of the compilation can continue. State dot type. I'm not language over that again. State dot create int. So now built-in type. Signed in 64. State.ast. Right here, and let's do that in this one as well. If the type is null pointer, we get the error and then we assume it's int. That's ironically also what real compilers are doing, so that's probably fine. And again, we need a position for that. So let's get a position. Uh-huh. And then we also need a position. So let's just get a position when we right here. Let's just get a position, scanner position. Okay. Needs to match previously specified return type. Sure, lambda is annoying. This argument is set next parent has type what? Alright, you want a non-const. Taking arguments for function call. Wait. Oh, right. You probably want a position. So let's get you a position. By just parsing it somewhere. Right, we already got that. With your arguments, right, you also want a position. No matching function to callback of type declaration. So declaration, we are somehow missing a position. Why are we missing a position? So we got the position. So we got the position of the decal specifier list and the inner declarator list. Why are you not? The invoke bound should really put some effort into this error message here. Compiler state type of specs, we're not getting a position. Dear error message, can you please tell me who's calling that? So I can fix it. Apparently not. Is it maybe issue? That looks okay. Apparently my filter broke. In instantiation, compiler.cpp to 35. Alright, easy. Let's pass you a position. I wonder what where the error message filter was broken there. Okay, all tests pass, and here we are getting invalid combination of base type and declarator. And then we are getting an assertion failure somewhere down the line because something doesn't handle null pointer. Right. Because turns out you're not actually an int anymore. That's annoying. You know what? Let's do something different. So we've got the type equals to state.askCreate. Right here. Let's just throw fatal error exception. Instead of attempting to recover. Right. And then in the top level compilation, we are saying if we are getting a fatal error exception, then we don't have anything. right? Something like that. That's a nice way of just, like, we won't get any subsequent error messages, but let's just say it's a fatal error, so we don't need that. Not ideal, but yeah, like doing proper error recovery and things like that, and also getting like good error messages instead of that one, which is like the bare minimum of an error message. Yeah. Okay, but we're checking for that now. Prevent arrays of incomplete type, incomplete element type. So back to what we're actually doing. So we want to support that. And we're getting an error message somewhere along the line of too many initializers for array. Right. We should also get an error message for incomplete object type. Because by this point, right? Because if we were to do that, this shouldn't, yeah, right. It's literally treated as a zero-sized array. So somewhere we are forgetting to checking for complete object types, presumably during variable declaration. So when we're passing a declaration, we're getting a type, we're getting it, right? So when we want to create a variable, I'm assuming we want a complete type to create a variable, right? So let's just say that if is complete object type of our type. I'm actually curious now. What happens if I do that? Invalid use of incomplete object type. So why is that error message triggered but not that one? Invalid use of incomplete object type. Right here. Oh, we're only doing it when we want to create a name declarator. Right. So we need to do that for all declarators. So let's just plug that message right here. Because an array can also be incomplete, not just a thing. Right, invalid use of incomplete object type, invalid use of incomplete object type. Okay, so that one works, and that one should stay in error, so that's fine. But that one should work. So we need to figure out the correct size at this point. So when we are creating an init declarator, right here. So this one called the non-init declaration. And at this point, we're getting the error message for incomplete object type. But if it's an incomplete array type and we have an initializer, then we're not doing that. So let's just say create non-init declaration, but pass you on bool has initializer. And you know what? Instead of let's maybe instead of has initializer, because we want to like get the type. But if we have an initializer and we have an incomplete array type, we want to set the size of the array type to the number of initializers. So let's, instead of passing a bool, let's pass you the size directly. Bool initializer count, right? And so if we don't have one, we pass 0. If we're having a single value, we're passing 1. If we're having a braced initializer, we're passing the number of things that we're having inside the brace. That should work, I think. Yeah, I mean, let's try it out. So if we're having an array type, type, and the So if we're having an array and that array is incomplete. But, so if we're having an array, the array is incomplete, but the initializer count, but we're having initializers. Then we want to set the thing. So type state.ask.types.build zero type forest node creator. So the element type be cloning the existing array element type, and then we're creating a new array type of the initializer count and the size, the element type. Let's just see when I got the order correct, of course not, so element type initializer count. Like so. And now obviously I need to call you. Initializer something like so here it's easy. Here we don't have any. But here I want to sort of like get the size of the thing. So init. So let's add a query like initializer count of which then returns similar like here. So if the empty init, then we still don't have any initializer. For braced init, we're returning the distance. Again, init initializer state end as a size t. And for an expression initializer, we're having a single one. And then we need iterator, I think. Let's see what that's doing. Cannot initialize, right? Seal of initializer count of the initializer. So that appeared to work, and we got an array with 3 elements. And we got an array with 3 elements. Nice. So let's try a couple of other things. What happens if I do that? Right, invalid use of incomplete object type, because it still has size 0. What happens if I do that? We're getting an array of size 1. That one still works. Too many initializers for scalar. Right. So apparently, we can correctly handle that now. And we've got an incomplete site, get the size deduced from the initializer. Deduce size of array from initializer. Now the last thing where we can use an incomplete type is as a function parameter. So like so. Inverted use of incomplete object type right here. So, used to declare parameter. So in a parameter, I believe that one should be pretty much straightforward, because I've got a separate thing right here. Inverted use of incomplete object type right here. So if we're having an array type, array type. We have an array, and array is incomplete. Then instead of an array, we are having a pointer. So types build data element type. We're cloning the element type of the array and instead returning a pointer. Pointer type to that element type. Which is like, I'm not sure why that's a feature of the language, but okay. Who am I to complain? And that one prints 3. Which doesn't appear to be correct. So, yeah, so we get the correct value. Do we still get the bug? We're getting a different bug. Okay, let's worry about that one later. So somewhere in passing that thing, so we are storing this is the function. So this function, we are storing 42 in there. So the initialization is correct, and then we're calling foo, and then we're calling print on the result. Why are we doing 2 pops? That's a bit weird. Okay. Why are we doing... That's like this point we're pushing an address on the stack. Anyways, okay. So we are storing the pointer in the parameter. We are getting its address. We are pushing 0. We are dereferencing it, and we are loading it, and then we're returning that value. Yeah, so apparently we're not getting the correct thing. So we're getting the address of the thing. So in the function we are getting... Wait, hang on, that's incorrect. We are getting the... So this one gets the address of the local variable. And then it stores... Right. So what we are printing here is again... we're printing the address of the parameter and not the value of the parameter. Is that only when we are... And it still happens when we're passing pointers. So it's not actually a bug related to the incomplete one. It's a bug in general in Kotlin. I guess so, because the function decal, right, the parameter, it's a pointer to an int, so that part is correct. So we can commit that. convert incomplete arrays in parameter to pointer. The parameter passing is all messed up of arrays. So in the call, like there's also this weird double pop which I don't understand. So in the call, we're getting the address of the array and passing that to the function. That part is correct, right? We want to pass the address to the function. So this one's doing, right? So this one gets the address of the array. Hang on. VST. So we're getting the we are missing it's another case of missing decay here. So what the subscript is doing is gets the array offset, like the this one gets the address of the array. This evaluates to the address of the array variable and not the address, right? This is the address of the pointer to the first element, not the pointer to the first element. I need the decay here. But then I wonder how that one works. Because in principle, we're not doing anything different here. Huh. Wait, why are we generating a decay here, but not here? I'm guessing... what happens if we use a pointer directly? So if we're using an array, we're getting a decay. We're using a pointer, we're not using. Okay, so pointer subscript, I don't have a test for subscript. Okay, so we broke that a while ago, apparently. I really need to write a lot more tests for this project. So the issue is that we're not decaying identifiers in the subscript operator when the type is a pointer. So subscript right here. We're doing array decay. No, we're doing L value conversion of the pointer. Not array decay, because we also want to do L value conversion. Hang on, that's probably also incorrect though. So now that particular tests. Right. Right, so now that one all works. But so the logic is, what L value conversion is doing is, if we're having a thing that is an L value, then we're getting the value instead. But do we want that in the subscript? What does the standard say? The subscript somewhere. Postfix operator right here. Yeah, right. This is equivalent to doing evaluating E1 normally. So we're doing L value conversion here. Except in the size of... Yeah, right. Right. So we need to do L value conversion. I just forgot to do that. Okay. Let's add a pointer test. Pointer 0. Need another number. plus 42 or whatever. What actually is 11 plus 42? 53. Okay, so do a value conversion in subscript operator. Okay. So that's that. And then we're having, I noticed a different bug somewhere in here. That's again the wrong target. Right, in a requested exit. So apparently something constant evaluation of the return thing or whatever is apparently not working. So what's going on here? So during the init CodeGen init, all right, I think I know what the issue is. I've noticed that one earlier. So after we're doing CodeGen init, we're leaving the address of the thing on the stack potentially. So this one. So in the scalar version, we're not doing that. Store consumes the address. Fill also consumes the address. Right. But if we don't have trailing initializers, then we're leaving the address on the stack of the last thing that we wrote to. So we need to pop that. 0. Now it works. Okay, that was an easy bug. And we're getting 1 as well. Is 1 the value? Yeah, that's correct. Okay. Don't leave address on stack during init. Okay, and let's write a test. Array. So we create an array of 3 elements initialized with 1, 2, and nothing. 0 is 1, 1 is 2, and 2 is 0. Then we write to the third element, to equal to 3. That one works. Okay. We can also assert that the size of the array is 3 times the size of an int. And the line of an array is the same as the line of int. Wrong target. Okay. That one still works. I can also dereference an array and write 11 in there. And I want to pass an array to a function. Right, so this one modifies array 0 and returns array 1. 0 plus foo array returns 2 and sets that one to 42. Okay. And then let's do that. Let's also do u. So what we implemented today, array 0 is equal to 42. And finally, this might not work. So I want to create an array of 3 by 3 elements. First one is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. That one, let's make it, let's give them different sizes so we can see which ones. So we've got an array of 2 elements like so. Okay. So we want array 0, 0 is 1. Alright, this one's X4 and we're getting access elements, so U. Apparently not. Okay, so apparently multi-dimensional arrays don't work. I wish I haven't tried this one out because I wanted to end the stream. Okay, let's see, tackle that next time. Okay, so we did a bunch of bug fixes for arrays, and next time we need to do bug fixes for multi-dimensional arrays. Apparently we're doing the initializers in the wrong order. And then we can start on strings, which are essentially just more arrays. So thanks for everybody who stopped by, and until then.